Okay. Delta T equals 0. If I look at a PV diagram, what's it look like? I go from here down to here, right? What else do we know? Delta T is 0. Give me something else.
V naught times V naught equals P final times P final.
Oh, okay, nice. P naught V naught equals P final. P final. All right, Matthew. He wasn't even here. Was he?
I wasn't.
What did you miss?
Like last Friday.
Oh, Friday. Yeah. Not Wednesday. I'm confused.
Changing U, internal energy is 0.
Delta U equals 0. Okay. What's the work? And the heat?
3/2 NR changing
That's delta U, but delta U is 0, right? For isothermal, isn't the work with a minus NRTLN?
Oh yeah, it's not.
I don't know what you were reading, Jared. That didn't sound right to me.
Okay. It was probably something else.
You were probably
That
reading.
was ADB.
We didn't do adiabatic. I don't think we did adiabatic.
You gave us like the equation.
I gave you the equation. We're going to derive it.
Yeah.
Okay. So, isothermal, right? Okay. Isovolumetric. Also known as isochoric. Right? What does it look like on a PV diagram? Vertical line. Right? Okay. What's 0? Delta V. Right? Change in value is 0. What else? The work is 0, because work equals minus PDV. Okay, that tells me what Q is. Q is equal to delta U. Equal to
3/2 NR changing T.
yeah, or N CV delta T, right? And CV is 3/2 R. Right? You guys with me? Okay. Iso Eric. What's it look like on a PV diagram?
Horizontal line.
Horizontal line. What's 0? Change in pressure. Okay. All right. What is delta U? Anybody remember? And
It's the same, yeah.
CV delta T. What is Q?
Changing
Delta
U
U
and
minus
CP delta T, right? Remember CP?
what's CP?
What's CP? You want to help Matthew?
5
5 halves R. It's the molar specific heat at constant pressure. This is molar specific heat at constant volume. Right? It's bigger for a constant pressure because the gas expands, so it takes more because the gas is going to release energy to the environment through expansion.
Is there no CT for constant?
Yeah, because delta U is 0, there's no change in temperature.
Like
You're not-
is CT a thing or is it?
No, just a,
Okay.
there's not a thing. Good try. Okay, adiabatic, that's the one we want to work on today. But, what do we know about it from what I told you? PV, isothermals, it goes from one isothermal to another, right? What do we got for it?
Q is 0.
Q is 0. What else?
Changing U is equal to what? Which is the 3/2 NRT. Changing it.
Oh yeah, forget it. Or NCV, right? Oh, this is interesting. This is what we're going to prove today. P naught, V naught
Yeah.
to the gamma equals P final to the gamma. So we're going to show that because, like, where did that come from, right?
And you told us gamma was 5 over 3.
Gamma is 5 over 3 or
CT over
CP over CV. right? If you do that, because 5 halves divided by 3 halves, 5/3. All right, question. Okay, this is a summary. Let's do it. Let's dig into this adiabatic process. And it's fun because we get to really do some calculus. We get to look at the ideal gas law. And we can do some stuff you probably did, I don't know, count 1 or count 3. It's going to be fun. Okay, adiabatic. So let's draw my isothermals in green. Right? Kind of like an isothermal. And we're gonna go from here to here. P naught, B naught, P final, B final. Right, make sense to you guys? Okay. So we want to start with the ideal gas law and the first law of thermodynamics. First law of thermodynamics, anybody remember? du equals what?
dq plus dw.
dq plus dw. In the ideal gas law, PV equals nRT. And during this process, what is changing? What are we allowing to change? Pressure, volume, and temperature. PV and T. So I want to take the ideal gas law and I want to look at the infinitesimal version. I forget what they call it in calculus. Maybe it's the implicit differentiation, I'm not sure. But it's like looking at the derivatives. Okay? So I can imagine, right, taking this and then basically kind of taking the derivative type thing, we call it the infinitesimal in physics. I have a change in pressure, I allow a change in volume, I allow a change in temperature. So the change in pressure, I would write dP. So I would have dP times V, but when I do a product, what do we have to do? The product rule, remember the product rule?
Sure.
What's the product rule, Matthew?
I said sure.
You said you remember, right?
No.
Oh, come on. Product rule from Calc 1.
Derivative of the first one times the second one.
Plus?
The second one times derivative.
Right, so this would be PdV plus VdP. Right, does that make sense to you guys?
Yeah.
Matthew?
Which one is the one where you have that, but then it's over, or like it's minus that?
That's the division rule.
That's what.
Yeah, but we're doing the product rule.
Yeah.
Equals nR dt. So I took a little change in pressure, a little change in volume. Oh, this should be dV. Oh my gosh. I got PdV times, or dP times V plus P times dV. There we go. Equals nR dt. Right, a little change in temperature. You see how I did this? This is what we call the infinitesimals. Okay? I'm just basically taking the derivative, essentially, right? A little change in this, a little change in that, a little change in that. Okay. And I need to look at the first law as well. So the first law is du equals dq plus dw, but u I can write in terms of t, right? What's u in terms of t?
3/2.
N CV times t, right? 3 has r, it's CV. So that means du is what? N CV dt, right? A little change in energy is coming from a little change in temperature. You guys with me? Okay, what's dW equal to? A little bit of work is equal to what? That should be in your notes. From like the first thing we did in the stuff.
I like the integral.
Yeah, but we want with the integral, we want the infinitesimal form. So we drop the integral sign.
Negative NRT ln VF divided by.
That was for a specific case.
Just a PDV.
So yeah, PDV. That was for isothermal.
No.
Right, but this is just in general, right? A little work, because the work integral, the total work is minus the integral of PDV. So a little bit of work is just minus PDV.
How are we gonna know the difference of what it's asking?
Huh?
How do we know the difference of if we need to find a little work or all the work?
Well, usually you calculate all the work, but you do a little bit of work for the derivation. Does that make sense? But in the end product, you want to figure out how much work total.
So we're going through this whole process to find the formula. Is this one of those like calculus questions that you're gonna put on your exam? Of like working through all this process?
Probably not, no. But I want you to see it.
Yeah.
I just don't want to give you the answer because
But we don't have to like know.
you don't have to go through this whole process. But you want to pay attention because
Yes.
this kind of process will be useful for when you do your engine stuff. Question?
How about this class? Is this physics with calculus part 2 or physics with applied calculus 2?
This is physics part 2 using calculus.
Hmm.
But it's called physics
With
with
Calc
calc
2.
2 because I mean it just sounds better.
Just wanted to make sure.
Yeah. You had calc 2, right?
Yeah. Well, I'm having it right now.
Oh, okay. Yeah. You're fine.
Yeah. I just wanted-
You're fine. Okay, you guys with me so far? Okay, so, what's DQ? We're putting all this stuff together, you see?
Very cool.
We're putting all this stuff together. What's DQ?
dW minus d.
Yeah, but what's DQ in this case? This case, what process is this? Sarah, looking all quiet over there. Adiabatic.
Yeah.
What does that mean?
It's thermally isolated. There's no heat transfer.
So what does that mean?
0.
What's 0?
The Q.
The Q, there's no heat transfer. So DQ is 0. Right? You guys with me?
Yeah.
So that means DU is equal to what? DU is also equal to the work. But that's equal to what?
Negative PdV.
Minus P dV. Okay, I'm putting all these little pieces together so we can build up the result. Right, this is good for you. All right, so look, I got PdV or DPV plus PdV. I'm going to switch this around because I like the derivatives on the end. So I'm going to write the DDP, okay? It doesn't matter the order. It's just a little easier to put the derivatives on the end. So VDP plus PDV equals NRDT. But NRDT, well, that kind of looks like du, doesn't it? It's close. So I just need to get rid of a CV and put in an R. I mean, you could write in terms of R, but let's do it this way. So we're going to go down here. I'm going to write du over du times R equals NRCV dt. I just multiply both sides by R, right? And then I divide by CV. So I can write that NR dt is equal to R over CV times du. Right, you guys follow that? That's not a very good R. Because I want to replace NRDT with du. Right? NRDT is R over CV du. So V dP plus PdV equals R over CV du. Did I lose anybody in that algebra? It's kind of
Yes.
okay. I want to get rid of NRDT
Why?
because I want to write everything in terms of pressure and volume. Because what am I looking for? The relationship P naught V naught to the gamma equals. I'm looking for a relationship between pressure and volume. So I got to get rid of temperature.
So you're trying to make that formula?
I'm trying to make that formula.
Okay.
So I want to get rid of temperature in here.
Yeah.
So I did that using du equals NCV dt. But I want NR dt. So I multiply both sides by R. So I have an nRCV dt and then divide both sides by CV. So I'm left with an nR dt. nR dt. That's what I'm left with.
Because nRDT equals your PV, right?
Yeah, equals all that stuff. Yeah, equals du. Yeah, nR dt. See?
Okay.
So I replace it. So I'm replacing nR dt with r over CV. Now CV is a 3/2 r. The r's are canceled. I'm going to keep it in. So I want to write this in terms of CV. I'm keeping it in r over CV du. Okay? R over CV du. But what's du is also what? Minus p dv. So I can write this as vdp plus pdv equals r over cv times minus p dv.
Your phone.
Your phone?
I'm like, yeah, let's keep going on. I keep getting notifications, don't I? There it is. Because I have smart glasses.
Oh,
So
really?
it dings when I get a notification.
Really?
Yeah.
What kind of glasses is this?
They're Alexa glasses.
Oh. It's awesome.
This guy.
Yeah,
This guy.
I'm cool.
Like Tony Stark.
I'm like
No,
Tony
like,
Stark.
Like Tony
no,
Stark.
like legitimately.
Alright. So now, notice I have a PDV here and a PDV there. So what am I going to do?
Cancel. No,
Put 'em
not
together.
cancel. Yeah.
They don't cancel, right? Because
Two
you got
PDVs.
So I'm going to put them together. So I get a VDP plus a PDV. This is negative, so bring it over, it becomes what?
Positive.
Plus
P.
R over CVP UV equal to 0. I better check my notes. That looks good. My notes look good. Okay. We can factor out a DV, right?
Yeah.
PDV.
So I'm going to erase up here. This will be useful, this stuff, even though you're not going to use it in, this class, when you get to thermal. This is a lot of thermal stuff, right? When you take a whole class on it, which is in everybody's degree plan. So, okay, VDP plus, I get a P plus an R over CV. Oh, I can factor out a P too, can't I?
Mm-hmm.
P times 1 plus R over CV.
Can you factor out the DV too?
Yeah, I'm going to put that on the end because I like the DVs on the end.
Okay.
Right, so I just factored out the P here and the DV. Okay. All right. Now I want to eventually integrate this thing, right? Because I got DP, TV, but I got the V's and the P's mixed up. If you see that, right? Do you see that? If I want to integrate this thing, I got a V times a P here, and here I got a P times a V. So I want to separate I want to get all the P's together and all the V's together. So how do I do that? I multiply both sides of the equation, because what I do to one side I can do to the other, right? By 1 over PV. It's a handy little trick when you're doing this kind of stuff. To separate out the variables. Get all the V's together and all the P's together. So of course, 0 times anything is what?
0.
Anything.
0. Right? 0 times 5 is not anything. It's okay. Oh, you're testing me. Okay. And now, if I multiply this through, what do I get for this term? Yeah, the V's cancel, don't they? You guys see that? See that? The V's cancel, I get a dP over P. So I've separated them. Plus, and then this term I get a what? I get a 1 over V, right? Because the P's cancel. Go 0. Okay, so this is looking really good. What did I do there? Oh, yeah, R. I can write R in terms of CP and CV, can't I? Remember that? Because what's CP equal to? CP is equal to,
Half star.
yeah, but in terms of CV it's. Because this is 5 halves, that's 3 halves. So 3 halves plus 1 is 5 halves, right? So CP is R plus CV. So I can write R as what? CP minus CV, right? Does that make sense to everybody? Put that in because that's how I'm going to get my gamma. So I got a dP over P plus a 1 over V, 1 minus CP minus CV over CV times dV equal to 0.
Is it plus,
Wait, what was R again? Sorry.
The gas constant.
Oh,
Question?
is it plus 1 plus CP?
Oh, 1 plus. Thank you. Thank you. Good eye. I was testing you. Okay. Oh, well now I can simplify that. Right? So I can write this as dP over P plus 1 over V. I can write this as 1 plus CP over CV minus CV over CV times dV equal to 0. But what's CV over CV? 1. So 1 minus 1 is 0, and I'm left with the CP over CV. Right, you guys see that? Okay, so I need space. Let's take that. Everybody's got this stuff, right?
Yeah.
Okay. dP over P plus, I get CP over V and then dV over V. CP over CV, dV over V equal to 0. Right? You with me, Mary? Because these went away.
Was that CV over CP?
CP over CV. That's CV over CV.
Okay.
From here, CV over CV, which is 1. And I just brought the V over here, because it's just multiplied. Now I can integrate. This is an easy integral now, right? What's the integral of dx over x?
ln of x.
ln of x. We've done that one before, right? We did ln. So this is going to give me what? ln of p plus CP over CV ln of v equal to a constant, right? Because the integral of 0 is a constant. I can do some math now, some algebra to make this look nicer. Remember our, well first, what's CP over CV? We're going to call that gamma. Right? So that's going to be gamma. ln of P plus gamma ln of V equals a constant. So gamma, now we don't have to write that all the time, CP over CV. And then, remember what some of our log rules, anybody remember our log rules?
If they're additive, it's the same thing as multiplying.
Yeah, so if I got ln of A times B, I can write that as ln of A plus ln of B. Right? So I'm pretty close to having the addition of logs. I just got to get rid of that gamma. But do you remember the other one? ln of A squared, what's that? You don't remember?
No.
Oh, okay. Let's try this. ln of A times ln of A, what's that?
ln of a plus ln of a.
ln of A plus ln of A, which is
Q ln of a.
ln of A. I can also write that as ln of what? A squared. So, are you getting a hint? ln of x to the n is what?
And ln of
ln
x.
of x, right?
Mhm.
So, okay, n doesn't have to be an integer, it can be anything. So I can write this as ln of p plus ln of v to the gamma equals a constant. Right?
Mhm.
I just brought it inside. Well, now I have the additional logs, like here. So we can erase this stuff. Okay. And if we erase that stuff, what do we get? ln of
P times ln of v over gamma.
equals a constant, right? So let's get rid of the ln. How do we get rid of the ln? E to the power. So e to the power of the ln, that gets rid of it. I just have p v to the gamma. Well, e to the constant is what? Just another constant. Right? So p v to the gamma is always a constant. So p naught v naught to the gamma equals p final to the gamma. So we derive that rule.
Could you always do that? Like multiply a constant by whatever you have in mind and call it a constant again?
Yeah, if it's a constant. If it's a constant you don't care about.
Because you're integrating, right?
Yeah, because I'm integrating, right. So didn't matter. Yeah. Pretty cool, huh? We did some calculus, we did some integrals, we did some derivatives. We used Adiabatic as Q is 0. It was a good process. Can we find a relationship between V and T? We did P and B, how about V and T? We could do that, right, Mary? Yeah, let's just use the ideal gas law for that. Remember, what's the ideal gas law? PV equals nRT. So all three are changing. I'm going to write P equals nRT over V. Right? That's true. Even if all three change. The ideal gas law is still true. So I can replace my P's with nRT over V. So that tells me that instead of P naught, I have nRT naught over V naught to the gamma equals nRT final over V final to the gamma. What cancels? The NRs. And V to the gamma divided by V naught, well that's what?
V to the power of gamma minus 1.
Yep. T final, V final, the gamma minus 1. So that's the relationship between T and B. And you could do P and T, just the same idea, but these are usually the two you use. This one and that one. Those are usually the two that you're going to use when you're looking at adiabatic processes. Let's see. Can we get work in terms of P and V on here? Just a try. We have a little bit of time. What was the work again? For an adiabatic process, anybody remember?
For the work?
Yeah, the work was, I'm just kind of
Or NCVT or
NCV
CNTT.
delta T, right? T final minus T initial, right? So NCV, T final. We could write T final is equal to what? T initial V naught over V final to the gamma minus 1, right? So we get T naught V naught over V final gamma minus 1 minus T naught NCV T naught V naught over V final gamma minus 1. And I can write T naught in terms of the initial pressure and volume, because usually you'll do that for adiabatic. So we can write T naught in terms of P naught and V naught. So we have NCV. T naught is what then? P naught V naught over NR, right? Something like that. Does that make sense to everybody? N's cancel. CV over R is 3/2, isn't it? P naught, V naught. Sometimes this is given a name. V naught over V final. Sometimes V final over V naught, I think. It's usually called R. It's like the ratio of the volumes, final initials, a compression factor type thing. So you'll see that when you look at diesel engines and things. So there's a lot of different things you can do. Right? And this is the adiabatic process, which is kind of the most interesting because all three variables are changing. All right, on Monday we'll build engines. Right, mental engines, not real engines. You know, bummer, right? And we're gonna see how they work theoretically. So I'm gonna do one engine in class, go through all the steps, all the analysis. I'm not gonna ask you to do that on the exam, but then next week's lab is you're gonna get in groups. I'm gonna give each group an engine, and you've got to calculate all the steps and find all the important pieces of that engine. Okay, does that make sense, everybody? That's what you're gonna be doing. So you want to know these steps inside and out. You are going to have to know all the steps for the test, because I'm going to ask, well, this gas is going under an adiabatic process. What's the work? What's the heat? And you know what I mean? How many moles of the gas? So you want to know all the steps for the exam. All right, yeah. Sounds good?